Okay, now it's time to start today's seminar. We are happy to have Doojin Kim as today's seminar speaker. So he'll talk about new physics in charged meson decays and its implication on the MiniBooNE excess. Please start.
Okay, so thank you so much for nice introduction, and also thank you so much for inviting me to the KIAS seminar and giving me a chance to share my recent research with you guys. Okay, so my talk today is basically based on my recent paper here in collaboration with Pascal Dutta, Adrian Thompson at Texas A&M University, and Tyler Thornton, the Richard Van de Water in the MiniBooNE collaboration. So, well, actually, I contemplated, how to organize the contents, hoping that you get a better idea on the big picture, the related to physics that we'll discuss today. Okay, so probably many of you heard about new physics researches at intensity frontier experiments and how good and promising they are. Of course, my talk is generally along the same line, but I'd rather tell you about a new or overlooked source of new particles, that is, the charged mesons. And then I not only try to demonstrate that with this, the new source, that you can come up with, like a plausible solution to the MiniBooNE low energy access, but convince you that this can improve sensitivity to your model in relevant experiments you prefer, or you can utilize intensity frontier experiments in a different way. Okay. By the way, so if you have any questions during my talk, please feel free to interrupt and ask your questions. Okay. So here's the outline of my talk today. In the next few slides, I briefly review motivations of intensity frontier experiments in terms of new physics researches and phenomenology, and talk about the couple of popular physics cases developed to those experiments. In the next part, I briefly discuss neutrino experiments as a class of intensity frontier experiments, as many new generation neutrino experiments are operational or will be operational in the near future. Given those the experiments, you naturally think about any opportunities for new physics researches or phenomenology on top of the neutrino physics. Okay, so in this context, I'll briefly discuss traditional approaches of studying new physics in those experiments. And the rest of the talk is about how to get new physics signals from the charged mesons. I showed that you can get new physics signals from the charged mesons very efficiently, and if the beam is focused, the signal from the charged mesons will be effectively focused. So there must be a good chance, to see the, to observe the signals. So if any new physics is, connected to the charged mesons. To convey the idea more effectively, I first review and discuss, the phenomenology of charged meson decays, and then to talk about implications on the MiniBooNE low energy access. So then I wrap up my talk with a few the take-home messages. So overall, the particle physics research has been performed at 3 different frontiers, so-called energy frontier, cosmic frontier, and intensity frontier. As suggested by this the Venn diagram, they are not independent but interconnected with one another and complementary to one another. So in terms of new physics particles, the energy frontier, the experiments like the LHC are best suited for heavy resonances requiring large energy for production. The cosmic frontier experiments detect any signals from the universe, digging out any hints to new physics out of cosmic wave signals. The intensity frontier experiments are more for fieldly interacting particles like neutrinos, extra-like particles, or dark matter. The particles under consideration are not much heavy, so energy is not an issue here. But their couplings to a standard amount of particles are typically very weak. Therefore, the basic strategy here is that you simply increase the statistics significantly, hoping that events of the rare processes take place within the given the experimental exposure. In this talk, I consider axion-like particle searches and low mass dark matter phenomenology as benchmarks. Okay, so let me quickly review the why axion-like particle and the low mass dark matter are motivated, especially at the intensity frontier. The first, speaking of dark matter, although a wide range mass values for dark matter candidates are allowed, much of the theoretical and experimental effort has been devoted to a very narrow region in the mass space, mainly motivated by the so-called WIMP miracle. Unfortunately, we haven't found any conclusive evidence of particle dark matter. Given that, you may alternatively look at other mass scales. So one possibility is MeV to the sub-GeV range. Indeed, they can be the thermally produced, and the dark matter candidates belong to this range. They can be thermally produced, and nevertheless they are less constrained by or less sensitive to many of the existing the searches. So that an enormous number of physics opportunities are still out there. Moreover, depending on model details, the complete dark sector scenario may have like new mediators and weak couplings. Therefore, this is another perfect example that you perform the searches in the intensity frontier experiments. For the axion-like particle, as we know, QCD axion is a viable solution to the strong CP problem, and the relevant physics programs have been extended to the genetic axion-like particles, and therefore axion or axion-like particles have received a lot of attention for a long time. They are one of the major drivers to motivate physics beyond the standard model, and they also can be dark matter candidates. Indeed, axion or axion-like particle searches lie in the low energy frontier. So many ongoing and proposed low energy high intensity experiments are potentially sensitive to the associated signals. Moreover, due to their like a feebly interacting nature, axion-like particles are another the perfect example for which the upcoming intensity frontier experiments will provide like unprecedented opportunities. Okay, so let me talk about the neutrino experiments because most of them feature high intensity and they will be operational very soon, as I mentioned at the beginning. So even some of them, start reporting their physics result, so you can immediately apply the ideas that I will discuss today. So I think it is reasonable to take neutrino experiments as benchmarks of the intensity frontier experiments. So broadly speaking, I would say there are three types of neutrino factories in quotes, depending on the typical energy scale of produced neutrinos. First of all, nuclear reactors can produce low energy neutrinos. Second, the beam-based experiments using stopped pions, like the coherent experiment, can produce medium-ish the energy neutrinos. Finally, the high-energy beam-based experiments, like the Doojin experiment, can generate high energy, the focused neutrino beam. I will briefly explain in a few slides how the neutrinos are produced in each of them and what the differences and features are, because such things are also closely related to the dark sector probe that I will discuss in the second half. Again, I'd like to emphasize that many lab-based neutrino experiments are operational or planned over the world to address one or some of the issues related to neutrinos, such as the number of neutrino species, their mass scale, and underlying mechanism to give masses to neutrinos, etc. So anyway, so what I show here is not fully adjusted. So I just locate these experiments where they just come into my mind just randomly. Actually, I tried to
Again,
go.
I'm sorry. What's
Yes.
Texono? Is it the location of Texono, right? In the map.
Is it? I guess Taiwan.
Oh,
No?
it's in Taiwan. I see.
Yes,
So
it's
you
in
didn't
Taiwan.
mention Juno and others.
Juno is in China, but yeah,
Right.
yeah, I didn't.
I
Actually,
guess that's
yeah, one of the Juno is I think somewhere here. I think.
somewhere.
Juno.
Yeah, there. I saw it. Yeah.
Yeah, Juno here.
Yes.
Yeah.
Yes.
So yeah, actually, I googled the neutrino experiments, just for curiosity, and found that in the Wikipedia, so more than actually the 50 neutrino experiments detectors or the telescopes were operational, are working, or will be in operation. More surprisingly, this list is not exhaustive either. So especially many of the future experiments are missing. So I would say that we are living in the era of the neutrino physics, and we all are invited to a variety of exciting physics opportunities reserved in the neutrino factories. All right, so now let's look at these neutrino factories a little more closely to see how the neutrinos are produced. Okay, so first, in the reactor neutrino experiments, the neutrinos are produced copiously in the process of the chain reactions. So the uranium or plutonium nuclei get excited, deexcited, or transformed to the different elements in the reactor core. Basically, the many of the nuclear reactions are understood in the neutron beta decay, shown in the upper right side of the screen. Through these processes, you get an anti-electron neutrino. The typical energy scale of the produced neutrinos is about 4 MeV, and they are not more than 10 MeV. Also, this chain reaction has no directional preference, and basically the flux of the emitted neutrinos is isotropic. So in principle, you could place your detector in whatever direction. Okay, so second, in the experiments using stopped pions, the neutrinos are produced in the following way. So basically, low energy proton, usually order, the 1 GeV, like beam, is impinging on a target, and then create the handful of the light mesons, as far as their production is kinematically allowed. So pions are light, so they can be produced. Eta mesons and kaons are, heavier than pions, so their production is very limited or even not allowed, depending on the beam energy. Basically, pions are not much energetic, so they quickly lose their entire kinetic energy while moving inside the target and eventually stop before they decay. And then they decay into the muon and muon neutrino. Now, the muon is also not energetic because the mass gap between the pion and the muon is not large. So, just like a pions, the muon essentially stop and decay at rest into electron neutrino, and muon neutrino. Since neutrinos are coming from these stationary sources, their flux is basically isotropic, which means the detector position doesn't matter much, just in terms of getting the neutrino flux, like the reactor core. So these are energy and the timing, the spectra of produced neutrinos in coherent, one of the experiments of this sort. So as I said before, the typical energy values are larger than those in the reactor case. Now, the timing spectrum is very interesting. So since neutrinos are coming from the stopped pions and muons, the timing when a neutrino hits the detector effectively imprints the lifetime of its source particle. So muon's mean lifetime is of microsecond scale, while charged pions is of tens of nanosecond scale. Therefore, if the detector comes with a good timing resolution, the prompt neutrinos from the pion decay can be distinguished from the delayed neutrinos from the muon decay.
Doojin, I'm sorry. Why do you
Yes.
say muon stopped? Muon has momentum, right?
Yes, muon has a momentum, but
Then-
the pion mass is 135 or 138 MeV. Then muon mass is 105 MeV, right?
Right.
So then the mass gap is the small. So
Right.
even
So
when
it moves slow.
yeah, very slow. So yeah, the muons are moving very slowly. But then the typically in this kind of experiments, the target is thick, and then the muons are losing energy inside the target, and then eventually stop.
I see. Within the target, they lose the energy.
Within the target, right?
Okay.
Okay. So finally, in the neutrino beam experiments, neutrinos are produced in a different way from the previous type of neutrino experiments. So this time, high energy protons are impinging on the target, creating a number of hadrons, mostly pions. This time, the target is not too thick for somewhat long-lived hadrons, the like pions and kaons, to escape from the target. Once they exceed the target, they enter the magnetic field region. Now, depending on the direction of the currents flowing in the magnets, either positively or negatively charged the particles converge, while the particles with the other electric charge diverge. For example, in the neutrino mode, So positively charged, the pions are converged, and each of them decays into the muon and the muon neutrino. Now, the muon also converges and decay into an electron and two neutrinos. Then a shielding material is placed before the detector so that unwanted electrons and surviving muons or mesons are observed, while neutrinos just pass through the shielding and reach the detector of interest. So basically, you have a focused neutrino flux, and the detector is usually placed along the beam line. These are expected, neutrino energy spectra at a dune-like experiment. Now you can see that the typical energy values of produced neutrinos around 2 to 4 GeV, which is even larger than the typical energy scale of neutrinos at stopped pion neutrino experiments. Of course, in the anti-neutrino mode, the negatively charged mesons are converging, and the resulting behaviors are similar to the positively charged mesons in the neutrino mode. Okay, so far we have seen that different neutrino experiments or factories produce neutrinos in different ways. The BSM physicists are wondering whether there are any opportunities in these neutrino experiments in terms of new physics searches. So let's see what are the known channels for those the purposes. So the people often pay attention to mechanisms of producing photons. So the well-known the mechanisms include energetic photon emission from the incoming particle beam, that is beam Bremsstrahlung, or the decays of the neutral mesons like neutral pion or eta meson. Depending on physics models of interest, the photons can be directly utilized. For example, you can produce external like particles or like a scalar through the so-called like a Primakov process, shown in this diagram, utilizing coupling of external like particle or scalar to photons. Indeed, a lot of groups, they have studied external like particle or the scalar searches in a variety of neutrino experiments like a sheet, phasor, sequester, etc. Or you can imagine production of dark photon via the conventional kinetic mixing with the standard model photon. So if the dark photon decays to dark matter particles, you can essentially perform the dark matter search. So this topic has been actively investigated in neutrino experiments, like stopped pion neutrino experiments and high energy, beam-based neutrino experiments, like DUNE and short baseline, neutrino program detectors. Okay, so the exciting existing efforts in the context of new physics searches and interceptive frontier experiments, especially neutrino experiments, are successful so far. But I believe this is not the end of the story, and there are still huge unexplored territory. Okay, so before moving on, any questions? Okay, so let's discuss new physics from focused charge mesons, beginning with the phenomenology of the charge meson decays. Okay, so this diagram shows the two-body decay of a charged pion into the lepton and its neutrino counterpart. So according to the effective pion interaction model, the derivative acting on the pion field couples to the electroweak currents. And then, after a little bit of, the algebra, you can find that the decay matrix element is proportional to, this expression here, resulting in the decay width here. Now, you see that the decay width is not proportional to the mass of the decaying particle or the mass scale, which you would expect in typical two-body decays, but proportional to the mass of the charged measure. Charged lepton. As a result, the decay branching fraction into muon is bigger than the branching fraction into electron, despite its reduced phase space. This is because this two-body decay is suppressed by a wrong helicity assignment, as suggested by the mass term in these expressions. So this behavior, can be understood in terms of the angular momentum conservation. So in the decay of the scalar positive pion, the neutrino is left-handed, whereas the positive, the lepton is right-handed. However, as you see here, the angular momentum in the final state is not zero. So this way of decay is highly suppressed. So if the charged lepton were massless, this decay wouldn't be allowed. But fortunately, the lepton has non-zero mass, and the decay happens through like a helicity, the flipping, conserving the total angular momentum in the process. By contrast, once you add another particle in the final state, so these helicity suppression can be evaded, since the additional particle allows for kinematic configurations to satisfy the angular momentum conservation, and the decay phase space can be fully exploited. As a consequence, a large enhancement in decay width is expected, actually. Moreover, in their decay to massive, the vector mediator, it is even more enhanced due to the existence of, the longitudinal polarization, resulting in contributions proportional to inverse vector square in the decay width. So if you think of, like a polarization vector, contraction, it comes with the 1 over, mass squared appears. So for example, the plots in the, the right-hand side show the branching fractions of three-body decays with the unit dark sector coupling, just for, simplicity. So you see that, as the mediator mass becomes small, the three-body decay, width, that can be much larger than, that of the two-body decays, or, the naive, the decay width, the branching fraction that you naively expect, in the three-body decays. And these enhancement becomes even larger with the vector mediators. Okay, so red ones. The kaon decays, they commit more enhancement than the pion decays, and the electronic decays commit more enhancement than the muonic decays, because the more phase space opens up. So here the block that could involve the various dynamics.
Hi, Doojin.
Yes.
Sorry for interrupting. I have a question. Can you please go to the previous slide?
Previous one. Okay.
Yeah, 80. So for the electron case, pion to electron decay. So do you know why this pion case is like this. Like you're saying for the vector case, there will be an enhancement.
Right.
Uh,
Yeah,
oh,
still, yeah, there's an
yeah,
enhancement.
it only happens below some mass, right? For the blue one, blue is the pion.
Blue is, yes, pion.
So, so why is it happening only below around 200 MeV? No, no, sorry, 20 MeV, right? That's or 2 MeV.
So this one?
Yeah, this one, yes.
Yes, yes.
That's 2 or 3 MeV. Yeah. So
So yeah,
then,
so I mean, basically, the chaos, much heavier than the mass of the mediators in this regime, right? So basically, oh no, it's a pion,
pioneer,
right?
pioneer.
Yeah, right. So once the final state, the lepton is electron, then you basically the use the full mass, the phase space, right? So the mass gap between the pion and the electron is huge. So now the even the scalar or the pseudo scalar can fully exploit, fully enjoy the phase space. So then by adding the one more particles, just like what I argued, that you can you don't need to you don't suffer from helicity suppression. But then now when it comes to the vector particle, well, there's sometimes it comes with the smaller the decay, I mean, branch fraction enhancement, but as you decrease the mass of the uh, uh, the vector mass, it comes with the huge enhancement because due to the existence of 1/mv squared, the term. Now, so your question is, okay, so here in the muon case,
Yeah.
so vector is always larger than the scalar case, but in the electron
Another
case.
thing, yeah, another thing is for the muon case, both of them are like you're decreasing the mass. Both of them are more or less going up. Uh, but here for the electron case, the scalar case is like almost constant for the lower mass, but the vector case is going up. So I guess for the muon case, also the scalar case will be constant after some time.
Right. So okay, so well, okay, so yeah, I guess that's that's sort of the details. But very roughly saying, in the vector case, so the dominant, I mean, the decay width is sort of dictated by the terms proportional to 1/mv squared. Okay. So then, as you decrease the mass, then 1/mv squared, the contribution becomes larger and larger, and then it gets, I mean, it shows in like some the non-trivial slope.
Okay.
But when it comes to the scalar or the pseudo scalar, that kind of term doesn't exist.
Okay, okay, got
Yeah,
got
yeah,
it. Okay.
yeah. So then once the saturate space, and that you essentially
it
get
becomes
the
constant. Yeah.
constant-ish, like a phase space, the branch fraction. Now for this one, it's actually, that's a good question. I haven't thought about this behavior in detail, and actually you are the first person to ask the question. But my guess is, yeah. So the still when I so when you look at the terms in the branch fraction, that some of the terms are still the helicity suppressed, which proportional to the mass of the leptons, and other terms are that other terms the proportional to 1/, the mass of the vector. So I think yeah, so here the electron case, maybe the helicity suppression term is also sometimes it becomes important, and then so here the helicity suppression is small, but the helicity suppression is the large, right? So maybe one of our MB squared term and the helicity suppression term are sort of competing each other in the vector case.
Yeah,
And then
also like as you said earlier, it also depends on the phase space, I guess.
yes, right.
Yeah.
So I guess that is I think I'm pretty sure it's related to the more detailed. Detailed.
Okay.
Doojin, don't you have analytic expression for the decay with font?
So I don't.
You don't
I
have
don't have. Yeah, but you can find
yeah.
the expressions in this page in this paper, for example.
Okay. Yeah. So as long as the phi the new scalar is light enough, the decay with kind of stay.
Yes.
Okay.
Sort of the constant.
Yeah.
Because again it doesn't involve 1/, mass of the scalar or
Right.
something like that.
By the way, the new scalar doesn't decay.
Actually, that's a good question. Yes, I will. That depends on the model details. But one of the scenarios I will talk about allows this mediator decays to a dark matter particle.
But you allow the new scalar couples to the charged leptons, right?
Yes.
So that means you, I see, depending on the mass. I see. Okay. Please go on.
Right. Yeah. So yeah, then that you have to think about him then like model details. So yeah, I mean Okay. Now so here the blob. So I just to show you the blob here. So the blob could involve various dynamics. For example, you could attach the mediator line to charge the lepton, neutrino, or the decaying pion, depending on the underlying model details. So if the vector is a gauge motion, the gauge symmetry generates the contact interaction, here. Moreover, the four models having the couplings to the quark contents inside the meson, so the QCD origin, structure-dependent contributions may arise. But in the rest of my talk today, we focus on the case where the mediators they exclusively coupled to the charged lepton, or at least these diagrams make dominant contributions, putting aside all the other complicated details. Okay, so now what is the beauty of this three-body decay channel of charge mesons? So let me highlight a few facts just for you to develop better intuition. So basically, the charged pion production rate is comparable to the neutral the pion production rate, as long as the beam energy is large enough. So you don't lose anything in the production rate. Now, neutral particles are obviously unfocused, while charged particles are focused in the Horn system. As a result, if you imagine the dark photon like the particle production using the mechanism that I discussed earlier, followed by its decay to let's say dark matter particles, the resulting dark matter flux from the neutral meson decays, like a spread widely in angle, whereas the dark matter flux from the charged meson decays are more forward-directed. Moreover, as I just argued, the charged meson decays can give the large branching fraction enhancement. So at the end of the day, the much more dark matter flux from the charged meson decays can reach the detector. Okay, so I think we are ready to discuss the implications of this charged meson three-body decay on the MiniBooNE axis.
Doojin, I just checked
Yes.
the PDG book and found the pion decay to muon plus neutrino plus missing energy is limited by 9
Yes.
to the minus 6.
Yeah. So I will talk about
Oh, I see. Okay.
Yes,
Please.
yes. But yeah, That's really the frequency. Yes, yeah, that's the one of the general things to check. Right. Great. Okay. So we are so impressed by this, the great potential of the charge mesons, and decided to apply this idea first to the famous the MiniBooNE low energy access. So needless to say, the MiniBooNE access is one of the observational motivations for new physics. A lot of explanations have been suggested, all involving neutrino sector physics. So very roughly, existing solutions can be divided into like three categories. So in the target horn complex, mesons might decay into a heavy neutrino through non-standard neutrino mixing, or the produced neutrinos might go through non-standard oscillations while they propagate to the detector, or new particles might be produced in the neutrino upscattering and decay to visible particles, mimicking the electron-like signature. Of course, some of the proposals are now in tension with the other experiments, but in general, neutrino sector involving solutions are popular over non-neutrino sector solutions, including dark sector solutions. And the question is, what's wrong with those, like dark sector solutions? Although in principle, it is possible to interpret the excess in the context of dark sector new physics. So in general, dark sector solutions assume the production of dark sector the signals from the neutral measures. For example, as shown in this, in the picture, so dark photons coming from the decay of neutral mesons and decay to dark matter particles. If that were the main source of the MiniBooNE access, the MiniBooNE off-target measurement would have observed events originating from the same source modulo the beam intensity, because neutral mesons just promptly decay in both target and off-target modes, irrespective of the existence of the horn system. However, the off-target mode measurements show no signal, and the dark sector solutions are less favored. Despite these major the challenging, so we realize that dark sector scenarios can get around this tension and be good the solutions to the excess using this charge meson decay channel. So let's see how that works out more closely. Okay, so we first consider the vector polar dark matter scenarios. Just for purposes of illustration, we consider dark photon type mediators, which couple to a standard model particle, matter particle, and the dark matter. Now, for purposes of generality, we allow for the existence of two different mediators. I talk about this possibility in the next slide in more detail. We further assume that there exists the heavier dark sector states on top of the dark matter, and therefore dark matter can like upscatter to a heavier dark sector state, say here the chi prime, or the chi prime can decay back into the dark matter chi once produced. Okay, so basically the charged ion or cation decays to a dark photon, which decays to a dark matter. Here we assume that a dark photon decays to the dark matter pair by 50%, and the other 50% is for the decay into an electron-positron pair, which is used for the detection part. Now, once a dark matter particle reaches the detector, it scatters off a nucleon or nucleus inelastically into a heavier non-acceptor state, chi prime. And then the chi prime promptly decays back to a dark matter and a dark photon, which subsequently decays by 50% to a collimated pair of electrons, which develop overlaid Cherenkov rings. Depending on the model details, the mediator here in the scattering could be different from the mediator responsible for dark matter production. So since the mediator in the scattering has nothing to do with the production of dark matter, in this double mediator scenario, these could be massless. For example, the scattering could be governed by a dipole operator, which is also the interesting possibility. Okay, now speaking of the simulation, this is a schematic flow of the entire procedure. So we basically begin with the production of charged measures. So we basically took a couple of the phenomenological models, the sample rank description, and a BMPT model-inspired Feynman scaling description, together with proper normalizations reported in a MiniBooNE paper, and generated charged mesons according to these models. And then we check whether their angular distance from the beam axis is in between 30 and 210 millibarians as a focusing angular range. And if so, we assume that they are perfectly focused and their momentum is aligned with the beam axis. Otherwise, we just ignore. We next check whether they decay before reaching the dump area according to the user decay law. Once they decay, we use MATLAB simulation and the sample events out of the MATLAB output to describe their free-body decay process in an event-by-event basis. And then the produced vector mediator decays to a dark matter the pair, and check whether a dark matter particle enters the detector fiduciary volume. Okay. We then generate the scattering events using the matrix element for this like off scattering the process. Finally, so we consider we took into account energy threshold, angular separation criterion, and detector efficiency when identifying the signal events contributing to the axis. Now, here's an example field. So the four plots are for the double mediator scenario, and they are visible energy spectrum in the neutrino mode, and visible energy spectrum in the anti-neutron mode, and the angular spectrum in the neutrino mode, and the angular spectrum in the anti-neutron mode, from left to right. Now, the dark yellow histograms are the combination of both known backgrounds, while the dark blue histograms show the signal events predicted by our vector polar model. What the latest the MiniBooNE data is shown by the black dots together with their associated the statistical backgrounds. And we also consider the systematics, the reported in the relevant the MiniBooNE papers, and perform the user weighted the chi-square field. So the resulting best fit values are summarized in the table below. Here I show on the example of the double mediator scenario, just for illustration purposes. We have found equally reasonable fit in the single mediator scenario, as shown in the table. This table shows this shows that there exist at least a few sets of reasonable parameter choices. So we are not showing the really best the parameter choices, but we just prove that there exist a reasonable parameter sets. Anyway, we actually performed parameter scanning for a few the parameter space slices that I will show in a few slides. Now you may as the Songchan pointed out earlier, you may immediately wonder whether the best fit values are okay with the existing bounds. So first of all, the parameter values should be consistent with the limits from exotic the decays of the charged mesons. Second, since we assume the dark photon type vector mediators, they should satisfy the limits of visibly decaying dark photons and invisibly decaying dark photon modulo the 50% to a 50% branching fraction that we assume. Finally, the model shouldn't produce too significant a number of events in the MiniBooNE off-target mode. As the off-target mode experiment reported, just one event. Well, for the first two, we can find respective coupling values that are consistent with these limits, while keeping the same coupling product that's shown in the the table in the previous slide. For the last one, we found that pi zero contribution is just 4 to 8%, which would yield the 2 to 4 events in the off-target mode, but they are consistent with the off-target mode measurement within the the measurement uncertainty. Okay, so as another the consistency check, you may wonder whether the parameter fits agree with the recent the Microboom result. Okay, so very briefly speaking, so Microboom reported the result in the photon channel and in the single electron channels a few months ago. The photon channel analysis constrains the neutral current delta resonance decay most stringently. Their result advocates that the MiniBooNE access needs a new physics interpretation. On the other hand, the single electron channel searches show that the data is consistent with the standard model expectation. So I will say the MiniBooNE access could be given by non-single electron events mimicking the single electron like a signature. So our model is not in the category of the single electron. Of course, the photon channel analysis would be a constraint, but the MiniBooNE data might not be sensitive enough to the access because of like a smaller exposure, smaller detector volume, and smaller photon efficiency. Well, the one interesting maybe the coincidence is that here the second beam in the one gamma 0 the proton channel shows a very mild excess, like the 18 events more. So our model also predicts roughly 18 events below 300 MeV. So maybe who knows, maybe this could be a hint to the MiniBooNE access. But I don't know, but it's surely an interesting observation that we keep, our eyes on. Okay, actually, the model that we employed to explain the MiniBooNE access may have predictions in other neutrino experiments. Not only neutrino beam experiments, but like a stop pion, 7th type, neutrino experiments. So the predictions for the neutrino beam experiments are very straightforward, and in general, then you could follow the similar analysis strategies as MiniBooNE is a type of the neutrino beam experiments. However, the stopped pion 7th neutrino experiments are somewhat tricky, and care must be taken. So most importantly, while we assume dark matter upscattering for MiniBooNE, it may not happen in 7th experiments because of the insufficient energy to create dark sector heavier state, as dark matter particles are coming from the stopped charged pions or nearly stopped neutral pions. Unlike MiniBooNE, elastic scattering there can be an option, as their detector energy threshold is small enough to detect even nuclear recoils. However, charged meson contributions are probably subdominant because now the resulting dark matter flux is not focused, but isotropic. As a consequence, conventional neutral meson, the channels become important again. I'd like to remind you that we have assumed that dark photon decays to a dark matter pair by 50%. So the dark sector coupling here should be as small as kinetic mixing associated with the mediator here. Therefore, if dark matter elastic scattering happens through the exchange of the same mediator here, probably the expected number of events would be too small. I mean, suppressions happens here and there. However, in the double mediator scenario, the dark matter elastic scattering happens through the exchange of the associated dark sector coupling here, right? In the double mediator scenario, the scattering happens through the exchange of the different mediator, and the associated dark sector coupling here has nothing to do with the dark matter production, so that it can be large enough for the 7th experiments to observe the signal events, which are potentially responsible for the MiniBooNE access. In addition, more energetic beam-based experiments like JSNS square can be sensitive to the signals coming from the decay of the kaons. Okay, so finally, let me briefly discuss the spin zero mediator case. So the model to be assumed is shown in the bottom of the screen. So according to this model, the charged meson can decay to the mediator via the muon lag here. Now, we assume that the spin zero mediator is lighter than muon and the Z prime, so that it can be long-lived enough to reach the detector. So inside the detector, the mediator goes through dark pre-Markov the process as shown here. So in other words, it scatters off the nucleus by a T-channel exchange of light Z prime, producing a photon in the final state, which can induce an electron-like signature in the MiniBooNE detector. Now, this shows an example fit in the scalar scenario. So again, the four plots are visible energy spectrum in the neutrino mode, anti-neutrino mode, and angular spectrum in the neutrino mode and the anti-neutrino mode from left to right. The dark yellow, the histograms are the combinations of all known backgrounds as before, while the dark orange histograms show the signal events predicted by our the scalar model. So you see that the fit looks better than the vector polar case, as also specified the chi-square value in the table. But this doesn't necessarily say that the scalar scenarios are superior to the vector polar scenario or the other way around. So I'm just trying to convey the message that various dark sector solutions are good enough to explain the access while satisfying the existing bounds, and therefore they are worth the investigating more carefully. Of course, it is also interesting to design strategies or propose ideas for distinguishing different dark sector solutions. Okay, really, finally, let me just show our scanning result in a few the parameter space slices as I advertised earlier. So these plots show like credible regions in which the parameter points are consistent with the MiniBooNE axis by 95% and the 90%. So yeah, that is not the benchmark. The parameter sets are not the only the sets of parameters. So actually there exists very large range of the parameter space. Okay, so let me conclude my talk. So the take-home message today can be summarized as follows. First, intensity frontier experiments that can provide great sensitivities to the signals of vividly interacting new particles. And overlooked the source, like focused charge mesons, was discussed as emerging opportunities and experiments. The MiniBooNE access that can be explained by dark sector scenarios using free body decays of charge mesons that are focused by the Horn system. Finally, a lot of applications still remain uninvestigated, so please stay tuned. And thank you.
Thank you very much for the nice talk. So let's open up for question and discussion. Any question?
So how seriously do you take the MiniBooNE access by itself?
See, the theorist.
Yeah.
That's actually a good question.
There are doubts and okay, so I want to hear what you think of.
Okay, so well, actually, in some sense, I'm very biased, and then so these days, I don't have the many chances to talk to the theorists about the MiniBooNE, partially because of the pandemic, and moreover, I have been working with the MiniBooNE collaboration members for a long time. So they're actually talking to me. Yeah, MiniBooNE access is real, and yeah, I think the access is there, right? But yeah, the question is, what would explain the access? And I heard that the data actually the other things inside the collaboration. I think that this solution can be a well. So I think the reason why the theorists lost their interest in the MiniBooNE is it's hard to find out the solution to the access while satisfying all the existing constraints and boundaries, etc. Right?
Yes.
I mean, they propose the ideas, and later other experiments disproved the model, and also like even the dark sector solutions have never been thought of the seriously because of the off target measurement data. But I think this model, I think this model is fairly reasonable, and then I can explain the access without major conflicts with the existing bounds and constraints, and also the more importantly, it can bring back the dark sector interpretation in the business of the minimum access. So I think the theorists, I believe they will to revisit the access again in the context of dark sector solutions. Hopefully they will recognize and appreciate this idea and overlook
Yeah.
mechanism.
Yeah, one more question is about the, for instance, Bell 2 may have chance to check this kind of new vector particle, new scalar particle. What do you think? Because they couple to the charged leptons, it is relatively easy to prove.
Yeah, I think so. Yeah. So I remember the Bell 2 is supposed to supposed to be sensitive to the dark photons.
Yeah, missing energies.
Yeah, who's the epsilon. I mean, the kinetic mixing parameter is very
Yeah,
small.
I think, for instance, mu on pair plus dark, the missing energy can be a good signal to check the scenario.
Yeah, so I think the Bell 2, the test this model pretty soon. I don't know whether they can also the test the scalar scenario that we consider here, because the behavior. Well, I guess in the right. So in the missing energy channel, the sensitivity becomes flat, right? So okay, so that doesn't. I mean, the mass value doesn't matter. Once, yeah, I think both of the scenarios that can be tested at the Bell 2, and yeah, it's gonna be very interesting. The Bell 2. Well,
Yeah,
I guess if this is
the ongoing experiment. So why don't we pay more attention to?
yeah, that's right. So if this is really true, then the Bell 2 would who knows? We'll discover something interesting.
Okay, thanks.
Okay, so any questions? So I have one more question about the pion to the lepton decay. I mean, three-body decays.
Yeah, sure.
So in that analysis, you use Procasses.
Sorry, I can't hear you.
In that analysis, you use the I mean the how you introduce the mass of the mass vector.
Yeah, that is actually a good question. So we haven't we haven't tried to construct the model in a consistent way. I mean, we just need to simply employ the existing models. But yeah, maybe this vector, if this vector is a the gauge motion, then we can get the mass from the by the spontaneous symmetric breaking or the other mechanism like a stupid the mechanism. So actually, related to the question, the decay width. I mean, mathematically, you will see the sort of like the singular behavior as you decrease the mass of the vector.
Yeah.
Right. So once they exist, the 1 over the mass square terms there, and then as far as the mass is, well, if the mass becomes really massless, then the gauge symmetry is really preserved, and you can actually consider the analog corrections, etc., and then all the the complicated dirty things are sort of cancelled. IR divergence is sort of cancelled, etc. So eventually you end up with a very small correction. But in the vector case, as far as mass is non-zero, it mathematically it is increasing and it keeps increasing, right? So I sort of remember one of the papers written by John Bickham and his company. They closely looked at that possibility, and then they they argue that well, in that case, some new physics scale, essentially comes into play. So then, you know, uh, there's some, the limit that you should apply this formalism, and then below that, the mass scale. So another, new physics comes in, and then the decay with calculation completely becomes, the different, etc. So I think, yeah, that's really good question. And so eventually, the once, let's say, suppose, the MiniBooNE access is, really confirmed, and then these let's say vector portal scenario is part of the solution, then yeah, so the people should, they carefully look at the model details, and then even the UV completion, and to identify, how the massive the vector acquires the mass term. Is it really from, like a symmetric breaking, or a mechanism, or some other mechanisms, etc. Yeah, that's my thought on that issue.
So in the graphs, I mean the scattering amplitude is diverged, right? I mean, so there should become the, how to say, some correction to the, I think, the graph. So can we roughly estimate which mass from the correction should be entered from, how to say, from the, in the context of UV completion? Or
Yeah, could you show the effective Lagrangian?
So if I have a Lagrangian here, so let's see. So is it here?
Mm-hmm.
Right. So that's, yeah, the Lagrangian.
Mm-hmm.
Uh,
These operators are all dimension 4. So it's not obvious how large is the
Right.
UV scale.
right.
Of
So
course,
this is,
yeah.
yeah.
Mm. To
This is
give
not
the message for dark matter and the vectors, probably you need to introduce additional Higgses, for instance.
Right. So yeah. So if the spontaneous symmetric breaking is involved, and then some, the scalar, scalar should be around somewhere, right? But so I haven't written the full Lagrangian, and that we haven't considered like a UV completed model. So we just, took out
Yeah.
the, the relevant the
Mhm.
part of the Lagrangian. But I think, yes, that is actually a very interesting question. And yeah, but unfortunately, I don't give you a idea about the scale choice. So the model doesn't say anything about the scale choice.
And maybe it's worth considering, for instance, U1 B minus L, or
Mhm.
U1 L mu and minus L E, I guess, to
Yeah.
for your purpose. Okay.
B minus. Well, the B minus area is, a bit tricky, and then even the mu minus LU also, the tricky, because actually that's very interesting question. So let's say, if the both leptons are gauged
Mhm.
under the same symmetry, then you have to consider. I mean, you have to include this contribution and that contribution together, and then you have to consider the interference effect as well, right? But then, so this guy is lepton, and this is an anti-lepton, or the other way around. Then their charge is opposite to each other, and then the enhancement here and then the enhancement here, they are canceled by the interference term. So so it's hard to get the large enhancement in the specific the class of models.
Okay.
So that's why that I zoom not dark photon, but dark photon like the scenario. So we didn't specify one model, something like that. But yeah, that's also there's some potential challenges you could encounter if you think of the
Doojin, do you have to allow pi at the V Bremsstrahlung from pion? I mean the third diagram.
Yes.
Do you
That is
need it
also possible.
or
So no, actually, this diagram is good enough. I mean, this diagram can give a huge enhancement. Okay, but this also they give additional the enhancement. I mean, I think the what if you consider this diagram and that diagram, they consider together, and then actually this gives us the large enhancement effect. But one again, the here, I mean, to be more precise, because you assume then, okay, so the new mediator is coupling to the pions, but the pion is sort of like a composite object. Essentially, it is coupling to a quark, and then you think about the QCD effects and etc. So these the vortex itself comes with some the form factor. Because this is not like an elemental particle or the fundamental particle. And then more than that, some the QCD or origin structure dependent contributions arise. So it's more complicated. But eventually they are sort of the subdominant effect. But that's that is sort of the complication if you assume this kind of the diagram. So that's why the in this study we didn't consider the contribution here, to just simply to avoid the complicated issues. But yeah, in principle, yeah, you can do that, and then that's not make it super difficult or super challenging. So I mean, it's just doable.
Okay, any
I have a couple of questions.
Yes, please.
First of all, you showed the slide. Could you go back to the slide about dark sector solution is not favored?
Yeah, yes, here.
Yes. So is this applying only for pi zero decay to gamma and neutron meson decay into gamma plus dark photon, or does it also apply to the class of solutions such as those proposed by Machado group and also Pascoli group in terms of the dark fermion?
So I don't know what you're having in mind.
So you are assuming I mean you are saying that the dark sector solution is not easy to accommodate MiniBooNE.
Right. So let's
my
say
question is that argument also apply to the solution proposed by Machado group and Pascoli group, which is I mean it's essentially the same particle physics model but with a different mass scale for G prime.
Yeah, okay, so that's a good question. So let's say, as far as I remember, the Pedro's, Pedro's idea was, let's say neutrino comes in, the neutrino upscatter to, the heavier, neutrinos, and which decays back into, the visible particles. So essentially that's not that, I wouldn't say that is not, dark sector solution. It's actually the neutrino sector related, the solution. So anyway, the signal is transported by neutrinos. And then the neutrino production is based on the standard neutrino production mechanisms, like a usual charge measure decays. So, I mean, so that's why their solution is not in conflict with the MiniBooNE off-target mode measurement, because all the charged pions and kaons, the charged mesons are essentially observed in the dump. Their signal is not coming from neutral particles. So I guess I don't know what model you're talking about for the Sylvia Pascalis.
Basically the same model, but in Sylvia Pascalis case, the G prime is much heavier, and so it is virtual, but it decay to E plus E minus.
Right.
Yes. So the question is whether G prime is on shell like in Machado's model, or if G
Right.
prime
Yeah.
is
Right. But again, so as far as I remember, I know the Sylvia Pascalis model, but as far as I remember, the her model also the coming from the neutrino sector. So
yeah, but I think it's a matter of I mean, how to call sterile neutrino, but basically in their scenarios, they introduce sterile neutrinos which has its own gauge interaction, like a dark photon. So in a sense, their sterile neutrino is in a sense dark fermion. So in that sense, their model also belongs to the dark sector solutions, I think.
well, but
yeah.
yeah, I mean, that also,
Okay.
yeah, I agree. That depends on the the scheme you to categorize the solution. So yeah, if you focus on the the particles which directly acting, I mean the explaining the access, maybe that could be sort of a dark sector solution. But I would say their dark sector particles are coming from the neutrino sector. But in our solution, it's nothing to do with the neutrino sector physics. So it's not coupling to either neutrinos or whatever. So neutrino doesn't change its flavor. Neutrino is not mixing to dark sector particles. It's purely coming out of the non-neutrino particles, right? But then their solution is the connected neutrinos, right? So sort of mixing, different kind of oscillations or.
Yeah, I think that that depends on how you interpret sterile neutrino. But
Actually,
let me ask a second question.
Yeah.
So, could you show this dark Primakov effect slide for dark Primakov?
Here?
Yeah. So why do you consider the G prime interaction here? The photon can also mediate, right, in the T channel.
Right. But then once you allow the f mu nu bar tilde, so then this scalar or the pseudo scalar immediately decays to photon pairs.
You assume only f prime f, but you don't assume action to AA. Sorry, action to gamma gamma.
Right. So we don't assume that because we wanted to this scalar or pseudo scalar to be long-lived enough to reach the detector.
Yeah, but in any case, you can have action. I mean, A coupling to gamma gamma, right?
That is true, but then then the signal flux will be significantly small.
Yeah. Small.
Right. So because the axion decays to photons before reaching the detector.
So right? Because of the other constraint.
Yeah, and also let's say suppose you might say okay, so why not explaining the excess using the decay of the scalar or the pseudo scalar. Yes, that's certainly a possibility. But then it's hard to explain the angular spectrum because the MiniBooNE detector covers 12, 20, or the 10 milliradians above the from the beam axis. Then the decay signal would populate in the very last beam in the cosine theta spectrum. But as you remember, there are many, the events in the other beams in the cosine theta spectrum. So that's why, the decay, the scenarios are less favored in general.
So finally, could you flash the slide which show the best fit parameters for your scenario?
So yeah, there are two things. Yeah, one of them is here.
I see. 17, 18, 14. Oh, in the double mediated scenario case, MV2 can be heavier than pile mass.
Yes.
Okay, I see. Okay, thank you.
Thank you.
Yeah. So you don't use a Skype, or you use or Zoom or email, or what is the easiest way to communicate with you?
Yeah, email is the best.
Email?
And then and then once we have if the Zoom is needed, then we can set up Zoom
Okay,
session.
I see.
Right.
Okay, thank you very much.
Thank you.
Any other question or comment? If not, let's thanks again to speakers. Thank you for the nice talk.
Thank you so much.
And thank you for attending. This is the
See you
talk.
soon again.
예,
Bye.
건강하게 잘 지내시고 바시카한테도 안부 전해 주시고 테르키한테도
예.
안부 전해 주시고 예.